I'm one of the coordinators of this lecture series. Our speaker for today is Dr. Тэйбер Ellison, and he is joining as we speak. So he will be here momentarily, and then we will begin in a few moments. So sorry for the delays.
While we're waiting for Tabor, Todd and I will take this opportunity to thank the organizations that have helped us. The U.S. Embassy and the U.S. Geological Survey have both supported our participation and encouraged us to do this lecture series. Of course, we have many thanks to the Association for the Conservation of Biodiversity of Kazakhstan. Without the assistance of Yanlik and Alyona, we would not have been able to provide this lecture series to all of you. They have hosted the series and created a website on which are posted all of the lectures and materials. So we are very thankful to them for their partnership. Chevron is funding the translation of our materials, including today's lecture. So we thank Chevron for that financial support. We would just like to remind people that the past 5 lecture materials are available on the ACBK website. And I know that we have many returning participants that are aware of this material and that website. Todd and ACBK and I, we thank you for your continued participation. For anyone that's new to the lecture series, and this is their first one, I believe Yanlik will put the website URL in the chat so that you can access that information after this lecture. There are 2 lectures left in our series after today's, after Dr. Тэйбер Эллисон provides his information. The last 2 lectures will be on February 6th and March 5th. They will cover regulatory and policy considerations. We will be joined by Dr. Jennifer Miller from the United States Fish and Wildlife Service for the second to the last lecture. The last lecture will be on best management practices, and Todd and I will present that one. And as I said, that will be on March 5th. So today we're presenting our 6th lecture, and as soon as Dr. Тэйбер Эллиson joins us, then Todd can introduce him. So has he joined yet while I've been talking?
I don't think he has joined, and I think we should just give him 1 or 2 more minutes. I know he is trying, and probably he is working with his computer, and he will be here very shortly. So, yeah.
Okay.
Please give us 1 moment.
We'll just go through some organizational information. The way that we have been running these lectures is that we will take questions at the end of the presentation. So if you do have questions, wait until the end and raise your hand with the little hand icon, or you can write them in the chat. So either way, we'll see your question. I guess, yeah, we'll be monitoring the chat. We also want you to know to feel free to contact, ACBK or Todd or I after the lecture is over if you prefer more of a one-on-one conversation or have a detailed question. Our emails are available on the ACBK website, and we would be thrilled to have a conversation and answer questions that you
Вон, да, и на него в сумке повесьте. Сломал он колесики.
Yanlik, can you mute Timoshenko?
Yeah.
Thank you. And I know Tabor is trying to join.
Yeah, it's joining.
Oh, okay. He had to reinstall Zoom. So, hello, Tabor. You made it.
Maybe.
Yeah, Tabor. Let us know when you are able to speak and make things work, and then I will introduce you. So, there he is.
Is here.
I apologize. I had the time wrong
No
or
problem.
later, and then when I tried to join, it just wasn't working, so I had to reinstall Zoom. But here I am.
No problem. So we have 50 people. We have 50 people on the call, and I am being asked to confirm my language, but we have 50 people on the call, and Jill has given some background on the lecture series. As she said, let's wait until the end to ask questions, and I will introduce Dr. Тэйбер Эллиson, who will then hopefully share screens and present on mitigation practices for renewable energy. Dr. Тэйбер Эллиson is an ecologist with an expertise in wind-wildlife interactions. In 2010, he became the director of the Renewable Energy Wildlife Institute and responsible for research initiatives. Previously, he was a vice president for science and policy and climate change at Massachusetts Audubon Society. He's also been at the National Science Foundation, the Rocky Mountain Biological Laboratory, and he has lectured at Ohio State University and the University of Colorado. He serves in a number of roles related to wind-wildlife interactions, including on the Scientific Advisory Committee of the Bats and Wind Energy Cooperative. Tabor holds a Ph.D. from the University of Minnesota, a master's in science from Yale University, and a bachelor's degree from Wesleyan University. And today, the topic of his lecture is on mitigating the impacts of wind energy on wildlife. So Tabor, let's try to share screens and turn it over to you.
All right. Thank you, Todd.
Perfect. We can see the PowerPoint. It's not in presentation mode yet.
Okay. How's that?
Perfect.
All right. Well, thank you very much, Todd. Thank you all for taking the time to attend this webinar. I apologize for being a bit late. I had the time wrong, and I just recently retired from REWI, the Renewable Energy Wildlife Institute, and had my computer reformatted, and I'm still learning what I used to be able to do that I have to start all over again. So apologies for that. So I will try to speak slower than I usually do and talk about, as Todd mentioned, mitigating the effects of, and I would say the adverse effects or impacts of wind energy on wildlife. And I know that in previous webinars, you've been introduced and got an overview of the types of impacts and how we assess them. And so the focus of this webinar is how we mitigate, or as I will define, avoid, minimize, or compensate and offset those adverse impacts. So in the course of this webinar, I plan to define how I will be using the term mitigation. I'm going to focus my attention on species of concern, in this case, specifically bats and raptors. They're not the only species, of course, that are adversely affected by wind energy development. But want to focus on these because, in part, this is where much of the attention has focused, both in the United States and in Europe. So when I talk about the available tools for mitigation, I will be focusing on what I think of as being unique to wind energy. Many of the aspects of developing any kind of human impact, there are common features, like when you're doing construction on a landscape and disturbing the soil. There are best practices that we try to follow that are applied across all projects. And so I'm not going to really get into those in any detail, but instead, as I say, focus on what's unique to wind energy. My emphasis will also be on what I call minimization, which I will define shortly. And the reason for that is that many of the unique aspects of wind energy impacts on wildlife are associated with the operation of the wind turbines. A talk presents some of the available research and what we're learning about mitigation, and then talk briefly about what I would call barriers to using mitigation. Why aren't some of these mitigation options not more widely used? So first, I will define mitigation and break it down into 3 steps, if you will, or what we refer to as the mitigation hierarchy. So the first step really is, under this hierarchy, is avoidance. And broadly defined, avoidance would be not taking the action or parts of the action. And in the context of wind energy development, this would be during the siting stage. And I will provide more detail and examples of each of these in the webinar. The second step assumes that the project, in this case a wind energy facility, has been constructed and is operating. And so minimization would be steps taken to reduce the adverse impacts of the operating of the wind farm. So it could involve limiting the degree or magnitude of an action or its implementation, which includes reducing the impact by changes in operation or by restoration of the affected environment. And again, I'll talk more about that. And then the third step, which in many applications, it can include multiple steps, but we call this compensation, or sometimes we use the word offset. But in the case of what we're talking about, compensation would involve replacing or providing substitute resources or environments. And typically, this step is intended for impacts that can't be avoided or minimized. And one way to think about this is that, especially as we talk about some applications of mitigation, a goal of mitigation can be to essentially reduce the impacts of a project to zero in its effect on the environment, or more specifically, species of concern. And as we're hearing nowadays, it can also be considered in the context of net positive. We're hearing that phrase more frequently, and we'll talk a little bit about that later on. So these actions, the compensation actions, can take place either on or off site, and they can involve monetary payments. Later on, I talk about in lieu fee programs, and that is a phrase that's used to describe a monetary payment that a developer can make to compensate for their action. And that payment would be used to cover the costs of an action taken by somebody else that would then serve as compensation. So the developer would not actually be taking the action, but they're paying for someone else to take the action. And so finally, compensation should measurably, and that's important, that term measurably, offset adverse impacts of a wind energy project. So let's talk first about avoidance. It basically has two components, or three, but the two primary components are what we call landscape level screening and site level screening. In the first instance, with the landscape level screening, a developer will be looking to avoid areas of high ecological sensitivity when siting, or the term we often use, prospecting, for potential sites for a wind farm. And so there's some obvious things to avoid, like protected lands, national parks, wilderness areas, for example, where development is precluded or not allowed. But the developer can also screen for the presence of species of concern, or for a term that we use, intact landscapes. And the example I give here is grasslands. In the US, one of the important landscapes that we have is the tall grass prairie, which occupies in the north-south axis, the central part of the United States, includes Illinois, Iowa, Missouri, and so on, and Kansas. And that landscape has been substantially modified by agriculture. And there are few examples of intact native tallgrass prairie in the US. And so there is a lot of interest in avoiding wind energy development in those remaining tracts of tallgrass prairie. A developer might also use landscape level screening to locate migration corridors or wetlands. This kind of analysis is generally what we would call a desktop analysis, where a developer is sitting at a computer and accessing data layers that like satellite layers showing distribution of landscape types. And I'll talk a little bit more about examples of that. But it's generally done in the office, as it were. Once the landscape level screening is completed, the developer, having presumably identified potential sites for a facility, will then do what we call site level screening. And this involves field reconnaissance, where biologists are sent out into the field and look for or attempt to confirm the presence either of critical habitat or the presence of species of concern. For example, critical habitat for endangered species or species of concern, like habitat, again, or the presence of an endangered species. Again, this is used to confirm the presence. And it is important to note that in such cases, you may not be able to confirm the presence of, say, an endangered species, but as we know, that doesn't mean the species isn't present. It's like confirming whether or not the absence of evidence is the evidence of absence, which is a popular phrase in the mitigation and wind energy and siting. So a third possibility is, which we can also talk about more, is what we call micro-siting, which when you're at this stage, you've identified a potential site, and you begin, the developer begins mapping out the location or potential location of turbines within the project footprint. And of course, one of the things the developer is trying to do is place turbines in the places where the wind is the best. And this also provides an opportunity for the developer to place the turbines in such a way as to avoid landscape features that might have ecological value or that concentrate activity and increase risk. For example, work done by Todd Katzner and his collaborators has looked at how raptors use topography, and this topography creating favorable winds for raptors to enable them to reduce energy use as they're airborne and migrating, for example. And a developer can identify those areas where use might be concentrated and avoid the placement of turbines in those areas. And the Fish and Wildlife Service has developed what we call the Eagle Collision Risk Model, which is a specific example of how a developer can adjust turbine siting away from areas of high eagle activity and reduce the predicted effects of a facility on eagles in the area. So over the past 10 years or so, there have been a lot of tools developed, what we call decision support tools, that support wind energy developers' ability to avoid ecologically sensitive areas. And the wind industry generally uses these tools, and they've developed their own proprietary tools for what we call fatal flaw assessment, that they identify something through their screening and says, this is not a place to develop a wind farm. And I just say something that I've noticed over the years with decision support tools, and I learned in preparing recently for this webinar, is that there's a lot of effort that goes into developing these tools, and I would say that they can be fun to create. It's a creative activity, pulling together all of the data layers, putting it into a format that's user-friendly, and launching it to great acclaim. The challenge is that these tools are based on the data available at the time. And as we know, particularly when it comes to distribution of species and ecological resources, this is a dynamic area of research. And so these tools can become outdated fairly quickly. And it's a challenge to keep tools up to date. And I would say, again, I'm just projecting my own view of this, that I think, it's not as much fun to maintain, and it's harder to sustain from a funding perspective too. To get the funding to maintain a tool is not as attractive as creating a tool. So just some examples of some tools. This is a tool developed that shows the distribution of leks of lesser prairie chicken. It's focused in this case on a particular species in the primary portion of its range in Kansas and Oklahoma. And prairie chickens are now protected in the US. And so this is an important source of information for a developer to try to avoid placing turbines near leks, and unlikely to get permission to site a project where there are leks. And as an example of the dynamic nature of these tools, one of REWI's partners cited a project in an area where there were no lesser prairie chicken leks. And then within a year or two, lesser prairie chicken leks appeared in proximity to and within the project, which of course created challenges for the developer, but also created a research opportunity to which has been studied to look at the effect of proximity of a wind turbine to lek persistence and the use of the area by this species. The Nature Conservancy has spent a substantial amount of effort in developing mapping tools and analysis under, for example, their Site Wind Right program. And you can see that this mapping program covers a large portion of the central United States, which is where some of the highest wind resources are. And it includes multiple data layers, as you can see in the legend to the left, including areas for whooping cranes, which is a critically endangered species, as well as intact natural habitats, or landscapes, if you scroll down this list, and lands of other biodiversity significance. The Western Governors Association, a few years ago, created what was called a CHAT tool, a crucial habitat assessment tool that could be used for screening. And this is a snapshot of the area covered by this tool. And in this case, the darker the color, the more crucial the habitat is for wildlife, with the goal of encouraging development of any kind, but in our case, wind energy development toward the lighter areas on the landscape. And I have to say that this tool is no longer being maintained. It's an example of what I was talking about earlier. other decision support tools that can be used for siting or avoidance, which are widely used for offshore wind, particularly in Europe, but also used for specific species in the US, are what we call collision risk models. They can assess, they're built on an assessment of activity of target species within a proposed area, and then using various kinds of models to both predict the risk and the potential impact on the species population, can provide a result that has been used to determine whether or not a project can go forward. And this is particularly used in the offshore environment in Europe. But the Fish and Wildlife Service has a similar model, their take prediction model, which is used to predict take of eagles based on pre-construction activity surveys. And I'm referring back to my discussion of microsighting. The results of this process of pre-construction activity surveys can identify eagles or areas of high eagle activity, and a developer can avoid those areas, and in so doing, reduce the take prediction for a potential project. And the service uses the results of this model to estimate the amount of mitigation that is required, the compensation, which I will talk about shortly. So I just want to talk briefly about some of the challenges with applying avoidance. To some extent, it can mean prioritizing one value, one of our values of what we think is important to protect, or the risk, prioritizing the risk over another. And an example that I would use is there is a priority, particularly among some conservation groups, to avoid intact landscapes. And, you know, that's an important goal. And at the same time, when we think about impacts to bats, which is also a large concern, the correlation between the risk to bats and the effect on intact landscapes isn't always strong. Some of the highest bat fatalities are in highly fragmented landscapes, in agricultural landscapes, for example, in Iowa. And so you may avoid one risk or protect one value while increasing the risk of another. And this is a challenge, and there's no easy answer to that question. It does, I think, speak to the difficulty in applying avoidance beyond obvious concerns. It's also difficult to predict risk, particularly to species, when we're not always sure what pre-construction information is useful. I've talked about, you know, the work that Todd and his collaborators have done with raptors, which is applied. But what other landscape features, for example, predict risk to bats? And so there's been some work put into this, but it's hard to determine how to apply what we've learned from that and how useful that information is. Collision risk models specifically are difficult to evaluate. For example, for years, we were collecting in the pre-construction bat acoustic activity under the hypothesis that bat acoustic activity predicted collision risk. And so far, we've been unable to make that connection, that there's no good evidence that bad acoustic activity actually predicts collision risk. Pre-construction, I want to actually make that clear. Pre-construction bad acoustic activity predicts risk. The same can also be said for measuring avian passage rates or activity. In the early years of wind energy development, radar was used to measure bird migration, and under the, again, hypothesis that high passage rates of birds as measured on radar would predict high collision risk, and that just hasn't been shown to be the case. Again, it doesn't mean it's not important, but we've just had a hard time showing from evidence that these measures are correlated. Third, evaluating collision models. When I think about the service collision risk model for eagles, it seems reasonable, and at a course level, some of our highest eagle fatalities are at projects that have high eagle activity. But the collision of an eagle is a rare event. So getting enough data to statistically evaluate models with rare events is challenging. And then in some cases, for example, in the offshore, data collection is impossible. We are not able to go out and search around turbines offshore to look for collision fatalities, although there's a lot of research going in to trying to measure collision fatalities for the offshore. Okay, so now I'm going to move on to minimization, and particularly focus on collisions, which is the impact of wind energy operation that is drawn the lion's share of attention. And there are two strategies for minimizing those collisions that involve either technologically based approaches or strategies. The first of these is curtailment, which involves shutting down or slowing turbine operation during periods of high risk. And then the second is deterrence, which involves use of audible or visual signals to alert wildlife to risk, with the goal of altering their behavior so that the wildlife avoids that risk. And so an audible signal, a bird is approaching a wind turbine, there's concern about collision, say for an eagle. An audible signal is generated with the hope of alerting that eagle, and so that it will alter its behavior and fly away and avoid collision risk. So I'm going to focus first on curtailment, which is where a lot of research has been conducted. And curtailment, the initial application of curtailment was based on the observation that bad activity decreases with wind velocity, so that the collision risk to bats, the way to summarize that, is higher at lower wind speeds than at higher wind speeds. At the same time, the thought was that wind energy facilities, wind turbines, generate less energy at lower wind speeds. So by curtailing the wind turbine operation at lower wind speeds, we might reduce the collision fatalities of bats. And the way this was applied was by what's called increasing the cut-in speed. So we define the cut-in speed. A turbine can spin at low wind speeds, but not generate any electricity. Most turbine manufacturers have set a cut-in speed or a wind speed at which a turbine starts to generate electricity. And this is typically 3 to 3.5 meters per second wind velocity. So if you curtailed the operation of turbines by raising its cut-in speed to 5 meters per second, the argument is that you will potentially reduce fatalities to bats, because that period of when bats are flying, mostly flying, you will the bats will not be killed. All the evidence that we have indicates that bats are not killed when turbine blades are not moving. And so restricting their operation will reduce bat fatalities. That's the goal. The way you curtail turbines to basically increase the cut-in speed is to feather turbine blades, changing their orientation so that they're parallel to the wind direction, and that slows their operation. And you can program a turbine to what we call feather its turbine blades to avoid turning at lower wind speeds. And this is a very effective tool. There's every study that has been conducted has shown that raising the cut-in speed, for example, to 5 meters per second, which I call the standard, it's become the common increase cut-in speed, reduces fatalities on average about 62%. And if you increase the cut-in speed further, you will increase the reduction, although it's unclear. The data are not sufficient to draw a strong relationship, but it is apparent that increasing the cut-in speed further than 5 meters per second will reduce fatality risk. And in what has been an unofficial policy of the Fish and Wildlife Service in Region 3 is that companies who are building projects within the range of the endangered Indiana bat can avoid having to get a take permit for this species if they increase the cut-in speed to 6.9 meters per second. And so it's an interesting example of where a minimization strategy qualifies in the service's opinion as avoidance. And so applying these, just also to be clear, increasing the cut-in speed, you do this during periods of high risk when bats are active. And so curtailment is typically applied from about around sundown to sunrise, with some buffer on either side during the periods when bats are active, typically in the US from mid-July to early October, and that varies from one region to another. And only during, as I say, the summer months. So during the winter, there's no curtailment for bats is generally not applied. So some interesting features about this is that even with raising the cut-in speed, one of the things that we've discovered is that turbine blades still turn rapidly enough below cut-in that they are a risk to bats, and yet they're not producing electricity. So back in 2015, what was then the American Wind Energy Association adopted a standard of feathering blades, and this, remember, is turning blades parallel to the wind below cut-in. And so adopting this standard, there's only one study, but it does suggest that on the one hand, yes, bats are still at risk below the speed when turbines are producing electricity, and feathering those blades can reduce risk to bats. And so this is a standard adopted by the wind industry in 2015. And at the same time, it's unclear how widely this standard has been adopted. And as I say, we don't know, don't have the data to indicate the effect it's having on collision fatalities at wind facilities, because it's hard to get the information to know whether a facility is feathering below cut-in, and being able to do that analysis. But it is an option that we know about, and the intention is to feather below cut-in. So some of the challenges, what we call AEP, or annual energy production, when the blades aren't turning, and you raise the cut-in speed, you are not producing energy. And a recent assessment shows you the range that has been estimated in terms of lost production. In some cases, it's minimal, but in other cases, that 3.2% doesn't seem like a large number, but it can be significant in terms of the financial viability of a project. And that margin is influenced both by the cut-in speed, which I think makes sense, and also the wind regime of the site and the number of nights. One of the issues that's happening too is that turbines are getting more efficient, and their rotor swept area, the blade length, is getting larger, which means they're able to produce more energy at lower wind speeds. So in regions of the country where you're putting up more efficient turbines, the consequences of that energy loss can be greater. Now, given that potential loss of energy, there is substantial effort to improve the efficiency of curtailment, which I'm defining here as the relationship between the fatality reduction and the energy lost. Minimizing the energy lost or increasing the fatality reduction, or both, increases the efficiency of curtailment. And so we've created or defined this term smart curtailment to increase the efficiency of curtailment, with the goal of maintaining the fatality reduction benefit and reducing the amount of energy lost. And it's basically based on the idea that when you're curtailing turbines at lower wind speeds, just based on the wind speed, and in this case, the time of year, you're curtailing the operation of turbines potentially when bats aren't present. We generally know that bats don't fly when it's raining, for example, but if you're applying curtailment based just on wind speed, you're not taking that into account. Bat activity also may vary at different times of year, particularly when bats are migrating. And so this kind of curtailment, where you're just curtailing turbine operation, we call blanket curtailment. And the goal here is to make curtailment smarter. And so there are a number of different approaches, one involving activity, timer, which was developed by Norman Doe and the Edison Electric Power Research Institute, placed acoustic detectors on turbines and used the measurement of bat activity to send a signal to curtail turbines during a period, and it was very effective. It was, first of all, operating at a very high cut-in speed of more than 8 meters per second. But it did reduce energy loss over controls and contributed to an 83% reduction in bats, especially bats, myotis bats, our little brown bat, for example, reduction, experienced a substantial fatality reduction. There are also model-based curtailment, smart curtailment approaches, where you create a model based on a series of predictors, wind speed, of course, and wind direction. What direction is the wind blowing? Temperature, other factors, time of night. And this model prediction essentially uses instruments at the wind facility to collect the data of the predictors, and then when certain situations are met that fit with the model, then a curtailment signal is sent out. Both of these options are an active area of research. And some of these projects, one of which I've been working on at REWI, evaluating a model developed by a turbine manufacturer, are wrapping up and should have results published in the next year or so. And again, I say these models, these options are showing some effectiveness. There's another option for curtailment, and we make the distinction here from smart curtailment. I use the term informed curtailment, where we typically in the past, the Fish and Wildlife Service, when a company is building a facility where there's eagle activity, will ask or require the developer to have a biomonitor program. So humans who might be in a tower who are scanning the skies for condors or eagles, and when one is detected, they send a stop or curtail order to the turbines in the area where the activity is occurring. And so that curtailment is informed by the detection of the species of concern. Now, there's a new technology that's been out for a few years called Identiflight, which can support automated curtailment. And the tests of Identiflight have shown that it has much higher detection rate than human observers. And here's a close-up of the Identiflight instrument, and it has 360 cameras that allow a 360-degree view, and then the binocular camera that you see on top will lock in on a potential target, identify it, and if it is an eagle, it will track it, and it tracks that eagle or another target species. And if there's a model built into the unit that says if the target gets this close to a turbine, it would send out a signal to shut that turbine down, hence the use of the phrase automated curtailment. As I mentioned, we've tested it for eagles in Wyoming. Todd has worked on some of those projects as well. And there's a suggestion that eagle fatalities can be reduced by as much as 85% by the use of Identiflight. There's a top of the world wind power in Wyoming, has a network of Identiflight units to cover the entire facility. And the change in eagle fatalities at top of the world wind power was compared to a nearby wind facility where Identiflight hadn't been installed. And so it appears to be very effective. It's very clear that it identifies or detects far more targets, if you will, eagles in this case, but it can be used to track other species. It's used in Europe for red kites, for example. But it is effective. The one issue with Identiflight, as we've determined, is that there's a much higher number of curtailments. And some of this could be due to the higher detection rate, but also to what I would call a high number of false positives, where signals are being sent out and the eagle is not, or is either not at risk, or there's a misidentification. For example, in Wyoming, turkey vultures often have been confused for eagles. There is work that's underway, research that's been going on for the past few years to understand better what constitutes collision risk, and the idea is to improve the efficiency, in this case, of the use of Identiflight. Another interesting feature and associated with this research is Identiflight is high quality optics. You have a golden eagle on the left and a red kite on the right. And you can use this information. The video that Identiflight collects provides data for research. And so you can study the behavior of, in this case, the kite or the eagle around the turbine to identify the high risk behavior, as I was talking about before. So moving on to deterrence, I'm going to talk about deterrence for bats and then deterrence for raptors. In the case of bats, as we know, bats identify, locate prey using echolocation. And the concept of deterrence is to broadcast what we call white noise from transmitters attached to the turbine to essentially encourage bats to go elsewhere, because the idea is that having that white noise makes it difficult for the bats to hunt, and they move away from the turbine. There are different ways in which those that white noise or ultrasonic sound that for bats can be produced. There are two systems: NRG Systems, which is a company based in my home state of Vermont, produces ultrasonic sound from vibrating discs. And in the photo that you're seeing here in the lower right, that it depicts what a NRG Systems deterrent unit looks like. GE, or General Electric, has also produced a deterrent that operates on the principle of compressed air that produces an ultrasonic sound. And deterrence does have effectiveness. The NRG Systems, when it's been applied, has reduced bat fatalities for some species by quite a bit. Free-tailed bats, a test down in Texas, and hoary bat, which is a particular species of concern in the US. On the other hand, however, other bats, eastern red bat, yellow bat, which I'm referring here to here as the Lasiurus bats, deterrence has shown no effect. And in some cases, it appears that fatalities have even gone up. At least, and that's not a statistical effect, but it does indicate that deterrence works for some bats, but not others. Similar result was found with tests of the General Electric systems. Not as effective as the NRG system, but hoary bat fatalities were consistently reduced. And as I mentioned, eastern red bat, which is a laziest bat, there was no effect. So this is a troublesome outcome that it's not consistent. There are some issues that may explain, although we're not entirely sure what the reasons are, why we're seeing these variations in species response. But one of the concerns has to do with the spread of the ultrasonic sound from the transmission source, which is on the turbine, and that it may not reach the blade tips, particularly in the large turbines that have longer blades. This graph here shows the attenuation distance, or where essentially a measure of how far the sound spreads and how it varies with the frequency. And the sound decreases substantially, and it's not unusual for rotor blades to be greater than 50 meters nowadays. And one thought and concern is that the deterrent may push the bats away from the interior portion of the rotor swept area out to the perimeter where there's still substantial collision risk. And we don't know at the moment whether that has something to do with why species like eastern red bat are not affected. And there are studies underway to look at this, and a paper just recently came out within the past couple of weeks, actually. It's one of the first papers of 2024 that talks about research about how bats variation in species response to deterrents. There's a question about whether or not combining deterrence with curtailment is more effective than just one of the strategies alone. And the suggestion is possibly. That's not a ringing endorsement. But one study showed, yes, combining deterrence and curtailment can increase fatality reduction. A study conducted in Illinois and published, as you see here, in 2022, showed that when the two strategies were combined, you increased the fatality reduction by the percentage points listed. Alternatively, a study funded by our Department of Energy found no effect. So again, there's a lot that we still don't know. There's hopeful information, but we don't have conclusive evidence. So now I want to shift to raptors on deterrence. A company called Liquen, Liquen, it's based in Spain, has produced a product called DT Bird, which we've been evaluating in the US and under a Department of Energy study. That study is wrapping up, it's completing, and we're writing up the results, and those should be available later this year. But the preliminary results suggest that deterrence decreases eagle activity in the rotor swept area by a significant percentage. It's not complete, however. And again, this technology works by cameras mounted on the turbine tower. As you can see here, these are the cameras that scrolling through these photos, and then speakers that emit a sound with the goal, again, of detecting a bird, a target species, and then emitting an audible signal to alert the bird, and with the goal of changing its behavior. And in the case of DT Bird, there appears to be some effectiveness. This isn't the only technology that I know of that uses deterrence for raptors, and it is used, DT bird is employed in Europe. Okay, so moving on to compensation. I want to talk first about habitat compensation. Again, this is something that generally is not unique to wind to compensate by creating or restoring habitat, for example. But there are some unusual features as it relates to wind energy, particularly when we're talking about bats. And for listed species, that I didn't define this term ILF, but it stands for in lieu fee programs that I mentioned earlier in my presentation. A developer can contribute a fee and to cause some habitat restoration for, let's say, Indiana bat or northern long-eared bat, which are listed species in the US. Or they can contribute to what we call mitigation banks, which are set up by a third party who use money contributed by developers of any kind to restore or maintain habitat for the affected species. And so these features, these programs are generally used for listed bats. Arguably, we don't know how effective they are. But the service, Fish and Wildlife Service, is willing to use those for listed species, which tend to be what we call in the US cave hibernating bats, because we have some idea of particular factors protecting hibernating sites, or what we call hibernacula is an option or strategy for protecting those species. Generally, fatalities of listed bat species, for the most part, is much, much lower than the fatalities for migratory tree bats. You probably heard on an earlier webinar that there are 3 species of tree bats in the US: hoary bat, eastern red bat, silver-haired bat, that make up somewhere between 70 and 80% of the fatalities at any project. And with a fatality level of that magnitude, as opposed to, say, 1 bat, northern long-eared bat per year, which is a not unusual take level or permitted level, the difference in the numbers, 1 versus hundreds, if not thousands, of tree bats at a facility, the ability to offset that take with habitat restoration is uneconomical, I think. And it's not really clear what limiting factors in the landscape can be compensated for in order to offset that large fatality level. Recently, for bats, the Fish and Wildlife Service released a letter authorizing the use of research on white nose syndrome as mitigation for cave hibernating bats. So white nose syndrome, you may be familiar, has substantially reduced the numbers of some cave hibernating species, like little brown bats and northern long-eared bats, where the loss or reduction is well over 90% in some areas. And so the Fish and Wildlife Service says that you can compensate for your take of these species by conducting research approved research on white nose syndrome. And this marks a substantial shift in the service on mitigation. In the past, they have not allowed research as mitigation, but they are allowing it or authorizing it in the case of white nose syndrome. And there are also, moving on, offset models. As you know, Julia's worked on with developing with colleagues the avian impact offset method. So I haven't really talked very much about this. It may have been talked about some, but the need to compensate for habitat impacts to birds, focus primarily on collision impacts. But there has been research that Julia's worked on with showing that some species of grassland birds are displaced or reduce their use of their habitat in proximity to turbines. And this can be a generate a need to compensate for that impact. And so she and her colleagues have developed this avian offset method, and it looks really promising. I think has a lot of great utility. So now I want to move on to what we call it the special case of golden eagles, compensation. And it's one of the few species, avian species, that the service has essentially called out or highlighted as having specific approaches for offsetting the predicted take of eagles at wind energy facilities. Our eagles, as you've heard probably, are protected under the Bald and Golden Eagle Protection Act, and the service has determined for golden eagles that there will be no net loss. So the status of the golden eagle population is such that the service has concluded that any additional mortality from any source will cause a population decline, and their goal is to maintain a stable population of golden eagles. So if a wind energy developer plans to build a project in an area where there is risk of collision fatalities or increased mortality to golden eagles, the company has to take steps to offset that predicted take. And the required mitigation ratio under the current rule, which is being revised as I speak, is 1.2 eagles saved or produced for each predicted take. So if a company has a permit to take an eagle a year, in other words, to have one eagle killed at its wind energy facility, if they have that permit, then it has to offset that take. And the key here is that that mitigation needs to be quantifiable and verifiable. And this is a rigorous standard that's not always applied to other forms of mitigation. But essentially, what it requires is that a mitigation option has a model, a verifiable model that quantifies the number of eagles saved or produced, and at a ratio of 1.2 to 1. Currently, the only approved option by the Fish and Wildlife Service is retrofitting power poles. A poorly constructed power pole can electrocute eagles and other raptors that roost on those poles. And the service there's a strategy, a known strategy for retrofitting or reconstructing a power pole to either reduce or eliminate that electrocution risk. And so this is a mitigation option, an offset option that the service says satisfies their criteria of an option that is both quantifiable and verifiable. And to improve the application of this mitigation option, the service has set up an in-lieu fee program that a company can contribute to offset its take. So the company, a wind energy developer, doesn't have to be in the position of retrofitting or being responsible for retrofitting a power pole operated by a separate entity, a utility company who's responsible for managing the power lines. So the company can buy advanced credits and essentially pay for the retrofitting of high-risk poles in the area of the management unit to offset its take. So there's been a lot of interest in developing alternative options for offsetting the take. And in the case of, just to back up a little bit, when I talk about the offset saving or producing eagles, the service has basically said, if you have a permit to take an eagle at your wind energy facilities, you can offset that take by reducing mortality from another source. So as a developer, I can offset a take of an eagle, the death of an eagle at my facility, by reducing deaths of eagles at a power pole. And there are other options that are out there. It basically is saying, what other sources of human-caused mortality of eagles are out there that we can offset? We know, for example, that eagles feed on roadkill, and in the carcass of a deer or an elk, which is on the roadside or in the road, can attract eagles who will feed on the carcass, and that puts the eagle at risk of being killed by passing vehicles. And they are killed by passing vehicles, sometimes in very large numbers. Another source of mortality is lead poisoning. Hunters go out, hunt game, deer, elk, and pronghorn, and they use lead bullets. They shoot an animal with a lead bullet, which fragments, and those fragments travel through the animal and lodge in the carcass, for example, what we call the viscera or the guts, which are removed by the hunter in the field. Those gut piles, as we call them, may have lead in them, and the eagles ingest that lead and increase their blood lead levels to the point where it causes mortality. So the challenge, though, with applying these, the options, the logic would say, okay, remove the carcasses from the road, or have hunters switch to copper bullets. That's the obvious mitigation approach. The challenge is, from the services perspective, is how do you quantify the effectiveness? How many carcasses do you need to remove from the road to save an eagle? With a power pole, a poorly situated power pole or a constructed power pole, they know that if we retrofit maybe 10 power poles, that we will save an eagle. But we don't know how many carcasses we need to remove, or how many hunters need to switch to non-lead ammunition. So we have been working for the past several years on developing models that enable us to predict the effectiveness of a mitigation option, whether it be substitution of copper for lead ammunition or carcass removal from roadsides, to estimate the mitigation credits that are available. And we've worked with a group of experts, Todd included, to both develop the model, and this is an example of what a lead abatement model looks like that Todd helped us develop. And then, so we have a model which describes the relationship of what we think are the important variables. So with the mitigation is removing gut piles or that have lead in them from the field, or substituting ammunition. How many deaths are avoided? And we then used experts to help us, these same experts, to basically say, okay, here are the variables in the model. Now help us define the quantitative or functional relationships of those model terms. And we go through a process where we ask the experts questions. For example, here's an example of a question where we ask our lead experts to estimate the probability of death of an eagle depending on its blood lead levels. And so we use those results to help us define the quantitative relationships of the model terms. And then once the model is completed, we run model simulations, and the output then provides the estimates of the offset as well as the uncertainty involved. And the output might look something like this, where on the top row is the percent of gut pile removal, 0 meaning all the gut piles are left in the field, and 90 means that 90% of the gut piles are taken out. And so we use information like this to predict or provide a quantitative and potentially verifiable approach to additional options. And the service is actually considering these right now. And the hope is that they will include them as approved options in the revised Eagle rule. Okay, so I want to shift gears here a little bit. I'm nearing the end, and talk about what I would call a non-traditional mitigation. And it refers to why we're building wind energy. It does provide electricity, which of course is important. And it also provides electricity without releasing greenhouse gases. And so it's generally accepted that we, in order to avoid the effects of climate change on humans and wildlife, biodiversity, we need to reduce our greenhouse gas emissions deeply and swiftly. And wind energy is seen as a major strategy for accomplishing that goal. And so there's been some interest for a while in whether or not the effects of wind energy on reducing greenhouse gas emissions can be considered mitigation by reducing the effects of climate change on wildlife. For example, bats and eagles, red kites, to some extent, and in some cases to a large extent, will be affected by climate change. Can you offset the effects of wind energy by somehow quantifying the benefit of wind energy development on climate change? And one way that we've articulated this, and Todd, I keep referring to you because you and I have worked on this as well, and you've done a lot of work in this area. We refer to this as the counterfactual. what if we don't build out wind energy? Typically focus on development is what are the consequences of building a project? And in the context of climate change, we're asking, what are the consequences of not building wind energy? Will renewables build out offset the adverse impacts of wind energy on wildlife? And we have a couple of different ways that we're looking at this. I've been working on a project to evaluate the effects of build out on the global extinction risk, which is one way of looking at the mitigation potential. And with Todd, we're thinking about looking into more species by species demographic analysis to look at the effects of wind energy development, the demographic impacts of wind energy development, and on the wildlife, both through its direct adverse effects and its effects on reducing the climate impacts on that species. So this is an example of the climate extinction risk, the kind of work we're doing. We're doing a carbon life cycle analysis for different energy sources, looking at temperature rise as it relates to CO2 concentration, extinction risk as it relates to temperature increase. This is all these, we're drawing on information that's available in the published literature. And then we're modeling how the rate of renewable energy deployment changes that extinction risk. So that's an example of what I was talking about. So a closing thought, and then I'm happy to answer any questions. I've gone through this fairly quickly, but I can say that particularly when we're talking about minimization strategies, we have strategies that are effective now. We know deterrence works. We know curtailment works. And yet these strategies, they are used in various projects along the way, but they're not universally employed. And what is preventing widespread adoption? What is preventing us from utilizing curtailment and deterrence at every project? The obvious answer is that there is a financial impact, particularly relevant for curtailment, because that affects operating income. What you hear from the industry is that they're hopeful that deterrence will be successful because the cost of deterrence can be factored into the development costs. But once a project is up and operating, curtailment can have an uncertain financial impact on the profitability of the project and potentially the ability to build future projects. And paradoxically, if a turbine is not operating at full capacity, we need more turbines to meet production goals. And so there's an increased number of turbines on the landscape, increasing risk. And so one way to overcome that would be to provide incentives for adoption. But oftentimes companies don't get credit for approaches or technologies that are still considered experimental. I mentioned Identiflight. Identiflight is being used more and more at projects in the US and also in Europe, as I understand. And at least in the US, the companies don't get minimization credit for using Identiflight at a project when it comes to their EGLE permits. This is a conversation that's going on with the service. And one way to work with that, there's the uncertainty, the experimental nature of the technology, is to see whether or not research on the technology or the approach can be factored into the mitigation. So in other words, doing research to refine deterrence, refine the use of identiflight, to reduce the uncertainty. If that can be credited, it might provide incentives both for the developer as well as wind developer as well as technology developers to continue to work and refine particular technologies. So with that, I'm happy to answer any questions, and thank you. I appreciate your attention.
Thank you, Tabor, for that fantastic review of mitigation. That's really amazing, and the details are remarkable. I know that it is late for many people, late in the day. Please feel free to ask questions if you have them. And Tabor and Jill and I can stay for a little while to talk about them. Tabor, there was one question in the chat about the cost of identiflight, and maybe that's a question you could talk about. It's not only identiflight, but some of the other technologies. And just before you answer that, there is, I know of at least one wind facility in Central Asia that is in the process of being built, that is planning to use identiflight and planning to use fairly large numbers of identiflight cameras at their site. So even though this has been used predominantly in the US and Europe and Australia, it is being used in Central Asia, and it is a real option in Central Asia. So yeah, the first question is about costs of some of these technologies.
Yeah. Well, first of all, thanks for mentioning that project in Central Asia, because I actually went at the conference on wind energy and wildlife in Croatia this year, talked with some people that are working on that. So thank you for bringing that up. And the short answer is, I don't know what the cost of identiflight is. I think to some extent it's proprietary. In my experience, the manufacturer, the company that makes identiflight, has tended to keep that information close. And because it often involves negotiations with a company. So I haven't seen that advertised. DT Bird, that is, in our experience in that analysis, the technology itself, it's, I'd say in the 4 figures per unit, and then there's the cost of maintaining and calibrating the system.
Yeah. Okay. Yeah, one little extra detail, identiflight is probably not something that an NGO would buy, but it's something that is designed into the cost of the overall project. And so that it's part of the financing and the bank negotiations. Tabor, there is one other question in the chat. Are there any data on birds or bats learning to avoid the dangers from wind turbines?
That's a good question. I think, well, I have to say the short answer is I don't know. And I say that not to mean that the information may not be out there, but it's harder to come by. I mean, there's some indication that whether it's learned behavior specifically or just call it natural behavior of raptors adjusting their flight paths and when approaching a turbine. There was a study years ago that was measuring songbird vocalizations that increased as they approached a wind facility. I haven't seen any other data or any, assessment of that work other than that result. So there may, avoidance may be a characteristic behavior of birds, at least. So not necessarily a learned behavior, but seeing a strange structure, something strange on the landscape that they're not expecting. And like communication towers, the concern and crashing into buildings, those tend to occur on nights of low visibility and where you can get high mortality events. So the premise is that if a bird sees the object, it can avoid it. Bats are a different story, as you may have heard on other presentations. There's some thinking that bats are actually attracted to turbines, and infrared thermal imagery show bats exploring the area around the nacelle of the turbine, that big box at the top where the generator is located. It's not entirely certain why. We've thought about this hypothesis of attraction for 2 decades, and I'd have to say we haven't really made a lot of progress in understanding the mechanism. There's an intriguing hypothesis out there right now that bats may scent mark turbines blades, but that is still to be investigated.
Okay. There's another question in the chat. Could you clarify the size of the area that can be covered by Identiflight? And I think that's one Identiflight, and for the audience, typically one Identiflight unit is not used alone. There are usually many that are put out. But do you remember how much area they can cover?
Well, it's pretty extraordinary what they see. I've been standing under an Identiflight unit, and the binocular cameras on top will swivel, and you'll look and see, I can't see what they're looking at. So they're very sensitive. I think Identiflight will state confidently that a unit can see out for about 1,000 meters. I think it can go beyond that. And the data that we have indicates that they're detecting and classifying targets beyond 1,000 meters. But you're right, at top of the world, that wind facility, that you have dozens of units to cover the entire facility. They overlap in their coverage, and they can operate as a network where they can pass a bird on to another unit, in effect, and issue curtailment orders in a network.
I think it's also the case that they can probably see some birds at 2,000 meters, but they see a lot more birds at 1,000 meters and even more at 500 meters.
Yeah, it's, the size of the bird, of course, matters. And one of the challenges with something like DT bird, which you can calibrate to a certain extent, but that has a harder time working with distance. And it's basically just based on the size estimate of the bird. And whereas with Identiflight, because of the binocular vision, they can determine that, oh, this is a small bird that's close. It's a kestrel that's close to the turbine, as opposed to an eagle that's further away from the turbine. And it can make that distinction with a fair amount of accuracy, good accuracy, I would say. Don't want to understate it.
So Tabor, there are two more comments in the chat. One is congratulations on your retirement. I think it's distressful for those of us who still want to work for you, but congratulations are certainly due.
Thank you.
And then this is a good question. There are two questions now. Both are really good. What type of mitigation can be implemented for non-echolocating bats? For example, fruit bats. Do you know of any?
Yeah, wow, that is a good question. Well, curtailment is what comes to mind. You know, I know that fruit bats are at risk, and there are fruit bat fatalities, but I don't know beyond curtailment, and I don't know as much about the magnitude or the timing of that risk. With you know, our bats, they're nocturnal, they're somewhat predictable, but you know, there is interesting work being done with weather radar to track movements of bats in the US and their prey to try and predict when you might have periods of high bat activity in the vicinity of a wind farm. And we've done a little bit of work on that. You know, I'm familiar with other work that's using that. And that may be, you know, something that would be useful for fruit bats, which are larger. You know, more of it. Yeah.
And of course, there's always the potential for habitat mitigation, habitat
Right.
alteration.
Yeah, I don't, you know, again, that for me, and I just, because I am not as familiar with the magnitude of the effect, when you're trying to offset one or two fatalities a year, that's a different level of investment than the hundreds to thousands a year at, for the tree bats. And, you know, I can't imagine trying to offset that.
So another good question, is there any research regarding the impacts of wind turbines on insects?
Yeah, there's certainly a concern. Yeah, and it's specifically comes up when we talk about in the US monarch butterflies, which are a species of concern at different times because they've had good years and bad years. But there, you know, there is a feature that companies have to clean insects off their blades to maintain the efficiency of the turbine operation. But, you know, I'm not aware of specific research to try and quantify that. We actually come at it from a different direction, which is thinking about why bats are around wind turbines. They're foraging on insects. Can you pull the insects away from the turbines and therefore pull the bats away? But, you know, specifically thinking of insects as a, you know, a class or as a category of species of concern, I have not seen that rise to the research level yet.
Yeah. Okay. Are there other questions? Does anybody, if anybody wants to raise their electronic hand and ask a question or have the translator help, please feel free to do that. If there are no questions, we should thank Tabor. That was a fantastic discussion. Thank you very much. I want to remind everybody that our next presentation will be from a person high up in the US government who will present about regulations in the US and really a theory of creating regulations. And that will be, Jill, I believe, February 6th. Is that-
Right, February 6th, the same time, right?
Yep, same time. And so we will send a calendar invite, and we would encourage you to participate. Please, if you have questions for Tabor or for Jill or I, feel free to send us an email. And you know, there's a lot of mitigation options that people have discussed, and a lot of interesting ideas that are out there. Jill, am I forgetting anything?
I don't think so. I want to thank Tabor. That was an excellent presentation, and happy retirement.
Thank you, Jill.
We will miss you.
Well, thank you. I guess. I don't know. I'm sorry you'll miss me. Maybe that's what I should say. I don't know. But I'm still around. I'm
Yes.
not disappearing completely.
I was going to say I'm not planning on missing him because I'm planning on interacting with him. Yenlik, are there other messages that we need to convey?
No, we have, I think it's good webinar. Thank you very much for Tabor for the discussing today.
You're
and
welcome.
our participants for joining us today. And we invite you next lecture. Thank you very much.
Okay, thank you.
Take care, everybody. Thank
Take
you.
care.
Tabor,
Bye.
thank you again.
Yeah, thanks, Todd. Thanks, Joe.